Awesome. Good evening, guys. I'm Jeffrey,
I'm Wesley.
And I'm Ashish.
and we're a couple of high school students at the Nanoscience lab, and we're hoping to shed some light on photolithography. So, photolithography, if you take just lithography and you look at the Greek roots, it literally means banging things together with rocks, which is kind of counterintuitive, but actually it's kind of like engraving something from another thing onto another object. So if you take photolithography, that means photolithography is on a much tinier scale, hence nanotechnology. To visualize this, you can think about it as, I guess, a stamp, and when you stamp into a wax mold, it kind of gives the seal of it. So photolithography is mainly used in microfabrication to pattern parts of a film, and in this case, it's going to be on a light-sensitive material called a light-sensitive polymer called photoresist. So once you have the light-sensitive polymer, you use chemical treatments to build on the initial foundation to form 3D structures by either etching into the original material or depositing more material to build like a 3D structure or model. And at one of our labs at CNSI, we experimented by creating a couple of very small wires using photolithography techniques. And here we see the inherent usefulness of photolithography because it's in everywhere. It's in your phones, it's in your computer screens, and a good way, and to think about it this way, Richard Feynman, one of the forefathers of nanoscience, once famously stated, "There's plenty of room at the bottom," and indeed, there was. Photolithography is what makes technology, like your phones, again, possible. Thanks to photolithography, thousands or even millions of tiny resistors, capacitors, or transistors can be stored onto a very tiny chip called a microchip, something smaller than a dime, which is pretty interesting to think about. It saves space and allows for immense complexity on such a tiny scale. And yeah, so on to Ashish.
All right. Yeah. So
It's the last day.
Sorry, they're
Thank you,
brothers.
Jeffrey.
They're brothers.
so along with that was like the main aspect of the experiment, but I guess the side aspect would kind of be to measure the resistance and the resistivity of the materials that we're actually creating. So just to define two terms before I actually delve and break down into the actual analogy. So resistivity is the actual inherent conductivity of how well a material conducts, like electricity. And resistance is the energy lost in the form of heat. And it also takes into account both the geometry, so the size and shape of the wire, and also the resistivity. So as you can see in the picture, there's these people that are trying to cross a river, and they can do this in two methods. So the first is by crossing a ladder. And the next method is by crossing the bridge, which is actually like shaded in. So basically you can break down how resistive or resistance, how much resistivity or resistance something has by the actual size and shape like I mentioned earlier. So the first thing we're going to compare are the thin ladder and the thin bridge. So if we look at the picture, there's more people on the other side of the thin bridge, showing that it's a better conductor. And the actual reason that is because, it has to do with the actual resistivity of the material, so it's just naturally a better conductor. And that's the reason why more heat or more energy is conserved in the actual process when electrons go through the wire. And the next thing we can compare is between the thin long wire and the thin short wire, the bridge, which is on the very edge of the right side of the paper. And basically what happens is that in the long bridge, there's more distance for the electron to travel. So there's a higher chance of interference going on. So that's why on the top of the bridge, there's only one person, where if we look at the shorter bridge, there's actually 3 people. So that kind of shows that the longer bridge has a lower resistance, so that means uh, it loses more heat. And the last thing we can actually compare is the width of the bridges. So we can compare the long thin bridge to the long wide bridge. And if we once again look at the picture, we can see that there's 4 people on the wide bridge compared with 1 person on the thin long bridge. And what's actually going on between these 2 bridges is that the wider bridge has a lower resistance, which means that it's actually losing less heat and conserving heat better than the thin bridge. So yeah, basically it's losing less heat than the other bridge.
All right, so the ideas of resistance and resistivity can be applied to photolithography. So specifically, a photolithography is a fancy word for patterning or transferring something from one surface to another. And this is good because it can save space, heat, and energy. And there are different types of photolithography, such as electron beam lithography, mechanolithography, scanning probe lithography, and photolithography. And among those, we studied photolithography. And photolithography is basically made up of 2 things, UV and laser. So then the copper wire experiment that we did is the UV one. And there are 5 different steps for the patterning. The first step is coating, which is done already for us, which was the copper film being covered with a light reactive polymer called photoresist, as Jeffrey said. The second step was masking, which made sure that the pattern was going to be generated. The third step was exposing, which we did by exposing the sample to UV light for 12 minutes. And then the next step was developing, which was putting the sample into a base to make sure that the only exposed portions are removed. And the last step was etching, which was the actual removal of the copper on the sample, or like the plate. And we also learned that there were 2 types of resist, like the other groups already said it. It was positive and negative. Positive resist being that after exposure to sunlight, it would be less soluble. The bonds would be stronger, weaker. Yes, weaker. And then negative would be the bonds would be made stronger, which we did the negative resist for our cyanotype activity in the afternoon with the blue paper and the plants. And last but not least, other applications of lithography can be used for iPhone screens, like Jeffrey said, camera sensors, and projectors. Yeah, that's it. Any questions?
I have some like basic questions. I can't read any of the words just because, I'm old and I have not great eyes. What are the people saying?
I don't think we can either.
No, I got it.
Yeah.
Okay. So the person in the middle,
Are they happy words or sad words?
oh, they're pretty bad. They're like, we're gonna get killed or something.
I'll help you out. It says we have to get across the river or we are going to be killed. Hurry up. That's
Yeah.
what the big speech bubble is saying. And so, if the other words are just people basically like failing at getting across because they're on things that are making them fail to.
Yeah, it's meant to show like resistance. So like the more people falling off, that means that's like a representation for heat being lost.
So I guess my question is so you guys described a bunch of things that was great about long bridges versus short bridges and wide bridges versus narrow bridges that all directly maps on to resistivity.
Yeah.
I am confused about ladders versus bridges.
All right, that's the material part, the inherent resistivity of the actual material. So if you can see, for the middle bridge and the bridge on the left, one of the ladders is short and one of them is longer. But the longer one is there's no one going across, which means that distance has. Oh yes, thank you. How do you turn it on?
Good question.
It's a test.
It's like
Oh, I got it. Okay.
Oh,
Sorry,
it's a
my
good
bad.
laser pointer.
Yeah, it's a great one. So, so the ladder is made of a different material than the actual bridge, which is wide. It's pretty strong. It's sturdy looking, you know. So people get across, but the people who go across the really long, narrow ladder, they just fall in the river and die. So, that's not good. But
Well, they don't
what
die,
I'm
they
trying to
fall
say
in.
is these two are very different materials, so they have different resistivity processes. And also, actually, in a speech bubble made by, I think this guy. Am I pointing at it? Sorry. Oh, it's kind of dying. But there's a person to your right. There's a speech bubble. It says, the ladder is so slippery. So that shows one of the other materials.
Okay, so that is the other way to convey that it is a different intrinsic kind of resistivity. It has a different baseline resistance, and then you can also modify it by width and length.
yeah.
Okay, other questions? Just because
Anish,
it's
no?
the second time that you've seen this topic, or the third,
I think
doesn't mean you don't have more questions.
So we talked about ways of diffraction, right? X-ray diffraction and electron diffraction. What do you think is one reason you would want to use electron beam lithography versus photolithography?
Well, I mean, it has like a smaller wavelength, so it's more precise. So like if you're going down to like a nanoscale, it's better to use electrons.
Yeah. What is the limit of the sort of the size of things you can make with light?
Well, I mean, if we're talking about like practical terms, it's like 300 nanometers, so like visible light. Well, I mean, actually, we can go down smaller distances, but
But you just sort of in order of magnitude. I'm not worried about
yeah.
about precise things. Maybe I should ask it differently. What determines how small you can go with any particular kind of light?
Like the wavelength, so like how long it is, how long the wave is.
And so for light like the UV light, what is that? What kind of size is that?
I'm gonna defer to Wesley or
Um,
my other teammates.
You already said it close enough for me.
you can ask my friend Siri.
Order of magnitude
you.
answer.
Well, I mean, I guess UV light has, I guess, a smaller wavelength. So it's kind of like the laser technology they use for lithography. I think that was one of the things that we mentioned. If I'm
Well, you gave a wavelength before. What wavelength did you give?
Like 300 nanometers.
Yeah.
Yeah.
So that's the order of magnitude. Few hundred nanometers
Yeah.
with visible light.
Mhm.
Can actually get down to like wavelength
Yeah,
over
smaller.
2. So a little less than the wavelength, but that order of magnitude. So if
Yeah.
you want 10 nanometers, you are not going to get there with visible
Yeah.
light.
Yeah.
That's the concept.
So a slightly different topic. So you talked about using the mask to create the pattern that you were essentially going to etch on. How do you get the mask made to that kind of precision at that time so that you can do the transferring? I understand once you have the mask how you get it onto the material, but somehow you have to make the mask. Did you learn anything about that?
Well, I mean, like we didn't learn about like the specific like manufacturing process behind constructing the masks, but I'm sure it has to do with like something like somebody else made in the lab, but we didn't like specifically learn about it.
Well, like what kind of mask did you guys use? Low tech.
I think we did the copper wire.
No,
bar.
your
Copper,
mask.
That was the
The
mask.
mask.
Oh.
Like, are you talking about like the material composition of the mask, or
What did your mask look like?
like it was black?
And what? Partly black?
Yeah, and it actually like blocked out light. So if that's
no,
what
it was
you're
like
asking.
a peel off. Then we
Yeah.
stuck it onto the.
She's asking just like,
thing.
what's the mask made of?
Yeah, I'm not actually sure about.
Just very generally, not like
Like a plastic, probably.
Plastic.
Like some
It's like a
polymer.
polymer.
Their mask was just printed in a laser printer, black on clear plastic.
Yeah.
Okay, so their mask was not high tech. It was black printed on transparency. A very
Was
black,
it
black,
barcode
I might
thing,
add,
right?
especially black, but it was just
a clear
black
piece
printed
of
on transparency.
paper or
But that's
plastic,
because
yeah.
your structures were just a little bit, they were in the micron scale, not in the nanoscale.
Yeah.
So I would say if maybe the question is, if you wanted to make a mask that was a whole lot smaller, that was in the nanoscale, how in the world would you do that?
I mean, I'm guessing that you'd use like some kind of, like you'd use nanotechnology to actually like manufacture it. So you'd use like an electron, like you'd use like electrons to actually like shine a beam of electrons and actually like make sure that the mask is like a small enough distance to actually cover like a small amount of like copper or whatever you're using.
Yeah, that's actually right. Use an e-beam writer to actually machine it with electrons in an e-beam writer to, and they're super, 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 super expensive, and we don't use those. But then you get to use them a lot of times, which is the whole goal. Okay, other questions? Okay, I'm going to ask a super quick one. You said at the beginning that this stuff is called lithography, and that lithography has to do with rocks, and you said it has to do with smashing rocks together, but it does not have anything to do with smashing rocks together, but the name lithography does come from rocks. So where's the rock part of lithography?
Oh, the
Lith.
it's actually
Like
graphy,
mono, yeah.
or it's lithos, which is
Yeah.
actually stone.
Stone,
Yeah.
yes, but and it is indeed based on stone. What aspect of that?
Well, you're kind of etching into the stone.
Yeah, the old way that you made copies of pictures is you took stone and you chipped a pattern into it, and then you inked it, and then you took the inked stone and you
like
pressed
a
it down on paper. So you transferred the pattern from etched stone, you put paint on it, and then you inked it down. And that there's still a very classic way of making art is to make etched stone things that you put ink on. And that's where the litho comes from.
So it's like kind of like a stamp, right?
It's a stone stamp, and you can make different pieces that you ink with different colors, and then you can stamp them down and make different colors together. And so many, in the not so long ago, there was a bunch of art that is made by, you make a lithograph and you make the stone things and you transfer it, and then you destroy the stone things so that there's a finite set of copies that could be made. Until recently, that's how great art, multiple copies, was always made. So, okay, good job.